Hello, how are you doing? This is Mike here, and in this question we're going to determine another volume of revolution. And this question is slightly different than ones we did prior because we are enclosing an area between two different curves. So the area is not generated by a curve and different axes, like the x-axis, the y-axis, that this is going to be the area generated by two different curves. So when I see this type of question and I don't have any bounds other than curve 1 and then curve 2, I tend to think that I'm not going to be using a disk method to solve this. I'm probably going to be using a washer method. This is probably going to be a washer method question. It tends to lead to a very good washer method question. So the first thing that I want to do when solving this and determining the area is that I want to find my intersection points. So I want to let y, which is equal to 4 minus x squared, set equal to the second curve, y, I should call this y1, and maybe this y2, which will be equal to x plus 2. So by setting these two equal together, then I can then determine where my boundaries will be. So that's going to help me a lot in determining how to graph this problem. So when we let 4 minus x squared equal to x plus 2, I'm going to go ahead and subtract 4 and add x squared on both sides, so I get 0, which is equal to a positive x squared, still plus x. 2 minus 4 gives me a value of negative 2. And in order to solve for this, we're going to factor, and we're going to get a value of x plus 2 times x minus 1. This is still set equal to 0. So we know that we're going to have two solutions of x equaling to negative 2 and a value of positive 1. So we have two solutions, when x equals to negative 2 and then when x equals to positive 1. So now we want to give an idea of what these curves look like. So 4 minus x squared is going to be a parabola shifted up 4 spaces, opening down. So I'm going to have something that looks like this. Oh, sounds horrible. So it's going to be symmetric about the y-axis. So I should do a little bit better job of indicating that symmetry. So here's my first curve, and then I have the line, so this is going to be in white, so maybe the next one in blue. I'll go ahead and show a line, there we go, of y is equal to x plus 2. So we recognize that we're going to have some intersections at these 2 points that I just drew, so we have an intersection there. So if I want to find my first value when x equals to negative 2, I'm just going to plug it back in. You can use either one. I'd rather use this guy. So we know that y will be equal to negative 2 plus 2. Y will equal to negative 2 plus 2, which is going to be a value of 0. So I really didn't draw this very well. And then my next one is going to be y is equal to 1 plus 2, which is a value of 3. So I'm going to have my points at negative 2 comma 0 and then at 1 comma 3. So this guy is going to be 1 comma 3, so we get 1 comma 3, and then this one should be intersecting over here. So I'm just going to redraw this. So I'm just going to fix this a little bit better. There we go. Delete that. Excuse me. So here we're going to have the other intersection point at negative 2 comma 0. So negative 2 comma 0 and 1 comma 3. Excuse me, are my intersection points. So here a little bit better, and this is going to be a little bit better. So now since we saw those intersection points, I can then determine where we're going to create this three-dimensional structure, and we're going to create it by rotating about the x-axis. So I like to put my corkscrew up there at the top, and now I can rotate this about the x-axis. So when we rotate about the x-axis, it's going to allow us to draw that three-dimensional structure. So let's go ahead. I'm going to move this down here a little bit, and oops, I have a little bit left over from my last problem. So I'm going to go ahead and rotate here, and oops, let me draw it with a Y with a white axis, make it a little bit easier to see. So here I have this guy right here, and this is linear. And then if I rotate about this axis, I will have something that looks like this. So it looks like a Pac-Man. And I should draw that as well in dotted lines here. So this is going to be my three-dimensional figure. So I have my three-dimensional figure, so let's go ahead and try to three-dimensionalize it. So here, as I rotate, I'm going to have a value that opens like this. Looks like that. And then inside, I will have, well, inside it will look something like that. And then I'm going to have an outer radius as well. So maybe I can try drawing my outer radius. I can try drawing my outer radius in a different color. So let me try drawing my outer radius in a different color. So I'm so bad at this, but hopefully you get the idea. So we're going to have an outer radius that will be right here, and it will look something like that. So so I get a nice looking bowl. It's going to be a Pac-Man bowl. So a nice looking Pac-Man bowl. So I don't like to get too into three-dimensionalizing the figures because I tend to make some mistakes if I get very crowded, but hopefully we can see that this inner portion here, this is empty. It's sort of like a lumen. It's empty. So this portion right here that I highlighted in green, this is going to be an empty portion. So the first thing that I like to recognize is that when I look at this, I have this lumen portion, and I know some of you that are probably taking physics as well, you're thinking lumen and light, but lumen anatomically means an open space. So like your liver has a lumen. I'm sorry, your intestines have a lumen. This is the open space inside the intestine. So I call this portion here is it's the lumen of the three-dimensional structure. So this portion here that I've highlighted in green, or that I'm redrawing in green, everything inside, this is an open space. This is not enclosed, but everything that's in the red volume is however a solid volume. So when we think of washers, we have an outer structure, and then we have an inner structure. So hopefully I can do this justice. So this inside portion from here to here, this inside portion is open. So this was a washer that we were used in construction. If we were building a desk, or if we were building a bed and we wanted to reinforce a screw, we would have this portion here and this right here that maybe I'll draw in red. This is actually I'll shade it in green. So this is all solid. So everywhere here is solid. This is very bright. So everywhere here is solid. Maybe I won't shade the whole thing. That might take a little too long. So everywhere that I'm shading here is solid, and then everywhere that is not shaded, well, then I have to shade the whole thing. Give me 1 second. So there we go. So this right here is solid, and then everywhere else is hollow. So if we want to find the area of this guy, we could find the area of the larger portion, and then we could subtract out the area of the inside. So we could find the area of the larger portion, which is going to be pi r squared of the larger ring, and then we're going to subtract out the area inside. And that's the same basis for the washer method to evaluate the volume that's generated by this dimensional object here. So notice here that since we're rotating about the x-axis, I'm going to define my radii perpendicular to the axis of rotation. So let's go ahead and look here. So in green, this will be my first radii. This will be the inside radii. And notice this is perpendicular to the axis of rotation. And then next, I will have my larger radii, which will go to my curve. And this is perpendicular to my axis of rotation. So let me go ahead. I've drawn a little bit more here, but I'm just going to go ahead and not draw the three-dimensional stuff so we can evaluate the radii a little bit easier. So we're going to evaluate the radii a little bit easier. So again, I have my Pac-Man. So the Pac-Man looks something like this. Then it looks something like this, and this has been a three-dimensional figure. So here, my inner radii, so this is my washer. So I have a washer that exists on the outside. So that's my large portion of the washer. And then I have the washer along the inside. So if we were to look at that, if we were to look at that from this site, we would then have this. We would have the outer portion, which is what I just draw, so that would be this portion right here, and then we would have the inner portion, which would be the inside radii, which is that right there. So if we look at this, we wanted to find the two radii. So this actually works out pretty nicely. Is that the inner radii is this to this. So this is the inner radii. So I'll call this R1, R1. So the inner radii is just going to be the value of y1. So this is just going to be equal to the value of y1. And that y1 is just going to be equal to that, I think that was, what was that? Forgot. X plus 2. So this is going to be equal to a value of x plus 2. So here, this is equal to a value of x plus 2. So from here to here, this is a value of x plus 2. So I go from anywhere. So if I were to draw from the x-axis to here, this is also going to be y1. If I drop from here to here, this is also going to be y1. So no matter where we are, we will always be going up a value of y1. My inner radius is a value of y1. How do we get to this top portion? So how do I get from the x-axis to the top curve? This is just a value of y2, and that value of y2, that was equal to 4 minus x squared. And if I go from here to here, this is also going to be 4 minus x squared. So from here to here, this is going to be a value of 4 minus x squared. So we've defined our inner radii and our inner radius and our outer radius in terms of x, and it works out really well because I rotated this guy with respect to x, and my radii are perpendicular to our axis of rotation. So the washer method integrates very similarly to the disk method. So I like just to write this out. So I'm going to integrate from some lower bound a to some upper bound b. So I'm integrating from lower bound a to lower bound b of pi times outer radius, outer minus inner, outer radius, and I'm squaring this, so I'm squaring my outer radius, and I subtract the inner radius, and I square this. Oh, I lost some stuff. I hate how it does that. And I'm going to integrate this with respect to x. I rotated the x-axis, so I'm going to integrate with respect to x. That's why I like the washer and the disk method. They integrate very similarly. They are going to integrate with respect to x because I rotated about the x-axis. So now I think to myself, where are we going to integrate? What's our lower bound to our upper bound? So this over here was 0, -2. And this one, what was this one? I think this was 1, no, sorry, this is backwards. This is -2, 0. -2, 0. I hope I drew that up here. Let me just check to make sure. Yeah, -2, 0. And this upper portion is 1, 3. So I have to look at the x variables, at the x values, which is going to be -2. We're going to integrate from -2 to a value of 1. We're going to integrate from a value of -2 to a value of 1. I'm going to pull this. I'm going to keep this pi out in front. Our outer radius is going to be this 4 minus x squared. And I'm squaring this. And I'm going to subtract my inner radius, which is going to be this guy, x plus 2 squared, and we're integrating this with respect to x. So the washer method and the disk method states that if I have an axis that's rotating, that's horizontal, I want to integrate with respect to x. You don't have to do it that way, but I may think it makes it a lot easier. So now let's go ahead and clean this up a little bit. So we're going to expand from -2 to 1, 4 minus x squared, so this will be 16 minus 8x plus x squared, so we're going to have 16 minus 8x plus x squared. oops, 8x squared plus x to the fourth. So that's x to the fourth. Sorry, this was 4 minus x squared squared. So we're going to have 16 minus 8x squared plus x to the fourth. And then we're going to subtract x squared plus 4x plus 4, because that's going to be this guy squared. And this is all integrated with respect to x. So we're all integrating with respect to x. Let's give us more room here. So now we're going to combine similar terms, negative 2 to 1. So I see I'm going to have x to the fourth up here, and that's going to be a positive x to the fourth. I'm going to have a negative 8x squared. I'm going to have a minus 4x. 16 minus 4 gives me a value of positive 12. And I integrate this with respect to x. That looks pretty good. So I'm going to keep my value of pi out in front. So this will give me x to the fifth all over 5 minus 8 thirds x cubed minus 2x squared plus 12x. And this is going to be bound from negative 2 to 1. Okay, we got some calculations to do. I'm definitely going to pull my calculator out for this one. Plugging in the upper bound, I have 1/5 minus 8 thirds minus 2 plus 12. And I'm going to subtract off the lower bound. So this will give us negative 32 fifths, negative 32 fifths. So that'll be for minus 32 thirds plus, so this will be minus 8 minus 24. Let me just take a second to make sure I do that correctly. So we get minus 32 fifths, yep. And 8, oh no, this is my, sorry, this is my, I knew something was wrong. So negative 2 cubed is negative 8, so this will be plus 64 thirds. I knew something looked wrong here. Negative 2 cubed is negative 8 times negative 8 is positive 64 over 3. So we get 4 times negative 2 is negative 8, and then lastly negative 12. I feel pretty good about that. Let's see what we have now. Let's clean this up a little bit again. Keeping that pi out in front, I got 1/5 minus 8 thirds. Negative 2 plus 12 is a value of 10. Plus 32 fifths minus 64 thirds. Negative 8 minus 24 is negative 32, but we're going to have a positive 32. Feel pretty good about this, so let's see what we got. So we're going to keep the pi out in front. So 1/5 plus 32 fifths is 33 fifths. Negative 8 thirds minus 64 thirds. Yeah, that looks like negative 72 thirds, like that. Then I get plus 10 plus 32 is plus 42. I think that's right. Yeah, that looks right. So we're going to have this equal to a value of pi. So we're still at 33 fifths minus 3 goes into 72. So we're going to have minus 24 plus 42. I think that's correct. 3 to 12. So that was good. So let me see what this is in terms of fifths. So we should have, oops, I don't know why this keeps doing this to me. It's just sabotage. So let's see what we got. And we got one. I think I have an error somewhere. Let me see. Something does look a little weird here. I don't think I did something right. So actually, I'm looking back and I do see an error. So some of you caught this error beforehand. Bravo! I did miss this error. So negative 8x squared minus 1x squared. This will in fact give me not negative 8x squared but negative 9x squared minus 4x plus 12. So all the rest of this is incorrect, and the computer doesn't even like it, so it just deletes it for me. So I don't know why it does that. So let's go ahead and reevaluate this. So I have x to the fourth minus, this will be a 9x squared, so this will be a 9x squared, and this will be a minus 4x, this is plus 12. Somebody looked funny to me. I should have just picked up on this. That's what happens when you're doing calculus wee hours in the morning after a long work week. There we go. So let's go ahead and do this a bit faster now. We're going to have the pi out in front, and this is still bound. What was that, negative 2 to 1? Yeah, negative 2 to 1. So we're going to have x to the fifth all over 5. I'm sorry about making that mistake. And this will give me minus 3x cubed. That makes that a lot easier. Minus 2x squared plus 12x. And this is going to be bound from negative 2 to 1. I like this a little bit better. Pi, so I'm going to have 1/5 minus 3 minus 2 plus 12. And then we're going to subtract off. So this gives us negative 32/5. So that gives us so plus 24. So that'll give us minus 8, and this minus 24. Oh, that's so much nicer. This goes away. Let's see, we got pi times 1/5 minus 3 minus 2 is minus 5 plus 12 is positive 7 minus, again, negative 32/5 minus 8. Yeah, I like this. So we'll have pi still out in front. 1/5 minus my negative 32/5 is a positive 33/5. Oop, I just lost some of the problem again. I don't know why it does that. So sorry. 33/5. And then we're going to have 7 minus a minus 8 is going to be 7 plus 8, which is the value of 15. Still times that pi out in front. So I'm pulling out my calculator for this one. So we're going to have 108. I like that better. 108 all over 5. So again, we're going to have 108 pi all over 5. So we have equals 108 pi all over 5. Sorry about that confusion there with the simple arithmetic error, and I apologize about that, but hopefully the calculus made sense to you.